Hello, I am Tutku Kolcu, and I'm going to talk about our recent work on cloud collisions in nearby barred galaxies. So I would like to start by showing you these two beautiful images from the PHANGS JWST survey, Lee et al. 2023. So on the left-hand side, you are seeing a barred galaxy, which has this extended structure that are from the Wolf stars, and that is channeling the gas in as this straight and slightly curved lanes. And the gas that's channeled in accumulates in the center and forms these structures like nuclear rings and disks in the middle of the galaxies. So we've seen in Matthias Ormani's talk on galactic rivers how this mechanism works, and I strongly encourage you to check it out. And on the right-hand side, you can see the unbarred galaxy, where the gas streams, as seen in the image, is pretty much spiraling all the way from outside towards the inwards. And similar to this barred galaxy, our own Milky Way also has a bar. So studies of Milky Way within the centromolecular zone shows these structures that are appearing in the position velocity diagrams. So these features are occurring really nearby to the centromolecular zone, where the gravitational potential of the bar is dominating. They have really narrow longitudes, and they have very wide, broad velocity extent, about 100 kilometers per second. So because these occur in a region where the bar dynamics is dominating, they have been long associated with being connected to the dust lanes. However, because of our embedded perspective within the Milky Way's disk, we cannot prove this. Further studies also studied these regions in detail and came up with the idea that these features that we are seeing is collisions of giant clouds. And they have similar extents in the velocity, and they were consistent with the models. So let's talk about what mechanism actually can cause EVFs. We can see in this movie of gas flow in a barred galaxy that you can see that from the both ends of the bar, the gas is being channeled in. It reaches to the center of the galaxy, where it accumulates and forms a ring-like structure. What I want you to notice is that not all the gas actually ends up in the center, and some of the streams are actually missing the center, overshoots to the opposite end, where it collides with the stream that was readily incoming from the opposite end. So a similar snapshot is shown in this Sormani study. On the left, you can see the more of a face-on view of the galaxy. You can see the ring and the incoming streams in red and green. So you can notice that the green one is missing the center and overshooting, which we labeled it as O1, and where it connects, where it collides with the other part of the bar lane is labeled as V1. And in the position velocity frame on the right-hand side, we are showing that this V1 structure appears as a really extended velocity feature over a narrow longitude, which was remarkably similar with what we've seen in the Milky Way. However, in order to confirm whether these actually holes, we had to look for external galaxies to see if these structures similarly occur in external galaxies, and this is not a coincidence, and whether this hypothesis actually holds. So therefore, in our study, using PHANGS ALMA and JWST survey data, we've searched for EVFs in nearby galaxies. So here, I'm showing you two examples from our survey. So on the left, you're seeing NGC 97, and on the right, I'm showing you NGC 3627. So in the middle panels, you can see the flux density, and on the top and right panels, you're seeing the position velocity diagram that were integrated over X and Y axes. And the regions where are marked with black rectangles are the regions where we see a CO enhancement and the extended velocity feature on the position velocity diagram. So totaling, we have looked at 29 barred galaxies, which were classified as barred based on their CO morphology within Stuber's 2023 work. And amongst these galaxies, we find 10, which corresponded about 34% of our sample. We found 10 that was exhibiting at least one EVF region. Within these 10 galaxies, totaling, we've actually identified 18 EVF regions. And what's remarkable it was that these EVFs were actually strongly absent in the unbarred galaxies, which supports that these features are actually bar-driven. To complement our ALMA study, we've also used PHANGS JWST data to search for incoming overshot streams. So on the right-hand side, you can see the JWST 7.7 micron image from MIRI, and what I highlighted the streams as in pink arrows. You can see there are multiple streams that has extending from one end of the bar to the other, and where I marked in blue rectangles are the regions where we see the EVFs is marked as the black rectangles in the position velocity diagram of ALMA. So amongst 18 EVF regions, about half of them were associated with these faint streams. So what does general properties of the EVFs actually tells us? So we've studied a bunch of different characteristics of these systems. So in order to do this, we had to isolate them from the ALMA cubes and fit their spectra to estimate their velocity extent, masses, virial parameters, and to see also about what region of the bar they actually occur. So within all these scatter plots, each point represents an EVF. So on the left bottom panel in blue, I'm showing you that the EVFs actually does not have any preferred location along the bar. So they had various different galactocentric distances. And they had similar masses and sizes to those found in Milky Way, which was quite consistent amongst different studies. And we've also seen that these features actually has really large virial parameters, which indicates that they are really highly unbound systems and that are far from equilibrium, which was consistent with the cloud collision scenario. We further studied the velocity extent, and we've seen that they had a range of about 30 to 70, and Milky Way were located about the higher end of this distribution. And we've seen that the velocity extent is actually scaling with the inclination of the galaxy, which supports that the difference in velocities we've seen is actually coming from colliding clouds rather than isotropic dispersion. So if the velocity extent was defined by random motions, we wouldn't see a correlation with the inclination of the galaxy. So the fact that we do see a correlation means that systemic velocity difference of colliding clouds is the main driver of this velocity extent. So similarly, we would also expect to see a similar dependence on the bar orientation. This is because the geometry of the bar contributes differently from the line of sight velocity. However, we do not see such dependence, which indicates that the general turbulence generated by the collisions also contributes to the velocity extent of these features. So in summary, we used PHANGS ALMA data to search for EVF analogs in external galaxies, which are analogous to those found in Milky Way. So we've found quite a lot of these features, and we've estimated that they are highly unbound systems consistent with the cloud collision scenario. Then complementing our ALMA analysis with JWST data, we've associated about 50% of these features that we've identified in nearby galaxies, having a faint stream, overshot gas streams that are extending from one bar end to the opposite end, supporting the picture we've seen from the simulations. So finally, I would like to mention that these structures that we found are some of the clearest example of cloud collisions, stream-stream collisions in external galaxies that we found. And they can offer unique laboratories to understanding star formation in these regions in detail as well. So hope you enjoyed this talk. You can check out our publication, and also for more interesting science talks, you can also follow the channel. Thank you very much.